Hello everyone, welcome to SS Talks Chemistry. I hope you all are doing great. So we were discussing the previous year questions of the CSIR NET exam, and in this now the new unit we are starting, that is your atomic structure and the quantum chemistry. All the questions that is from the year 2011 to the year 2025 we are gonna discuss. Okay, and this video is gonna be the part number 1 in this. So let's begin. The very first question, it is from the CSIR exam conducted in the June month of the year 2011. The question, it says the unnormalized hydrogen atom, its 1s wave function is given by this, which is psi 1s is 1 by root of the pi into the xi upon the a naught raised to the power of 3 by 2 e raised to the power of minus of the xi r upon the a naught. If where the xi value is equal to the 1, the energy is 0.5 atomic units, minus of the 0.5 atomic units. If we use the normalized wave function of the above form, with the xi value is not equal to the 1, the average value of the energy of the ground state of hydrogen atom it's gonna be. So what scenario it is given? A wave function of the 1s orbital is given. Corresponding to this, if the xi value we are keeping it to be 1, the energy in that we are getting is minus of the 0.5. Right? What if this xi value is not equal to the 1? And in that case, what is gonna be the energy value? So for this, we should know the formula for the energy that you have and the corresponding wave function for which this energy term we are getting, that also you observe it. So psi for the 1s orbital, we know it is 1 by the root of pi into the z upon the a naught raised to the power of 3 by 2 e raised to the power of minus of the z r upon the a naught of it. So this is the wave function. Now corresponding to this, the energy in different units you get it. We get the energy minus of 13.6 z square upon the n square. This is in the units of electron volt, right? And this is equal to minus of the 0.5 z square upon the n square in the units of atomic units, right? Now this energy we need it. Now instead of the z, they have used a new symbol. Just this is the difference. Here the xi value, it is equal to the z only. Okay, if this is equal to 1, in that case energy value is minus of the 0.5 atomic units, right? Now they are saying if the xi or the z value, it is not equal to the 1, so let's assume that this value we are having, that is 1.4. Okay, so that makes the energy value in this case we will be getting minus of the 0.5 into 1.4 square upon the 1 square, considering the n value is 1 only. Okay, so on solving this we get the value which is minus of the 0.98 atomic units of it, right? So now this value of energy that you have got, this value is smaller as compared to the previous one, right? That means if z value it is increasing or it is other than the one we are having, in that case energy value is gonna be less than the minus of the 0.5 atomic units, right? So based upon this, option C is becoming to be the right answer, because this is less than the 0.5 minus of the 0.5 atomic units. Okay, next this question, now again the same paper. The constant of motion is defined by which of the following equation? So first term is, what is meant by this constant of the motion? Constant of the motion, it means we are having a quantity which is not changing with the time. Quantity that does not change with the time. Change with the time. These are called as the constant of the motion. Now in the quantum, we know that for every observable, like the kinetic energy, potential energy, momentum, position, we have the corresponding operators for them, right? So that means here the quantity, it refers to that observable quantities. Now observable quantities, they are gonna have some operator. So let observable has some operator which is some a. So this could be the operator of the kinetic energy, potential energy, position, momentum in any of the direction like this, any of the operator it could be there. So according to the Earnfest theorem, this constant of motion is defined. Earnfest theorem. It's Earnfest theorem, according to which if I take the average of what thing, the commutator of the Hamiltonian operator with this observable that you are considering it to be in the constant of the motion, if this average value it is equal to the 0, then that particular observable it will be called as it is in the constant of motion. Okay, so based upon this, the option B it becomes the right answer. I hope it's clear. Now next, this question. The Hermitian conjugate of the operator d by dx, that is called as d by dx dagger, is actually equal to. So direct from the properties of the Hermitian conjugate, we know d by dx of the dagger, it is minus of the d by dx of it. So option A is the right answer. Okay, next. Again, same paper. The unperturbed energy levels of the system are E naught, it has the energy which is 0, E1 it is 2 and E2 it is 4 in this. The second order correction, so we have to find the second order correction which always comes out to be a negative value. We already know this, right? Second order correction to the energy for the ground state. Okay, in the presence of the perturbations which has been applied in the ground state, V10 it is 2, V20 it is 4 and the V12. So this is not of the ground state, so its value is given just to confuse us. Right, now I know the energy term that you find it for the second order correction to the ground state. This is gonna be V10, that is the perturbation. Its square we have to take it. In the denominator it is E0 minus of the E1 of it, plus of the V20, its square it will be there, upon the E naught minus of the E2 of it. Like, right? So this term is not included because the ground state term is not included in it, because it's not the perturbation for that. Right? Just substitute the values now. So it is 2, the square of it, 0 minus of 2 plus of the 4 square upon the 0 minus of the 4 of it. So this comes out to be as minus of the 2 minus of the 4, that becomes the minus of 6. So this is gonna be the energy correction of the second order perturbation, that is minus of 6. Option A it becomes the right answer. Right, so from this condition only that you are having the negative value, you could eliminate two of the options directly. B and C was eliminated. Out of the A and D only, then based upon the calculations we just have to find this answer. Okay, next, again from the CSIR exam of the June 2011, the energy levels for a cyclobutadiene molecules are alpha plus 2 beta, alpha, alpha and alpha minus of the 2 beta. So this is my cyclobutadiene. This is the one. Now the Frost cycle, based upon that, to see the energy levels representation, it is drawn like this. The lowest one it is alpha plus 2 beta. These two levels are alpha and the alpha, and this level it is alpha minus 2 beta. Right, the delocalization energy we have to find it out. So firstly here you see total how many pi electrons, 2 from this and 2 from this, total we are having 4 pi electrons in this. So they are filling, it will be done like this. So total energy it's gonna be 2 times alpha plus of the 2 beta plus of the 2 alpha of it. Right, so it becomes 2 alpha plus of the 4 beta plus of the 2 alpha, that means it is 4 alpha plus of the 4 beta of it. So this is my total energy. Now the delocalization energy it is equal to total energy, so E total minus the number of the ethylene units. Number of the ethylene units. So with that you have their energies, you have to multiply it with the number of ethylene units. So this will come out to be 4 alpha plus of the 4 beta minus of, now here the ethylene units, that is the ethene molecule, CH2 double bond CH2. So you can see one this pair we are having and one is this pair, so it is 2 times of it. So this is 2 times, and the energy for one of the ethylene unit, it is 2 alpha plus of the 2 beta of it. This value it is coming. So on solving this we will be getting, so on solving this we get, it was 4 alpha, it was 4 alpha plus of the 4 beta minus of the 4 alpha minus of the 4 beta of it. So these values they are cancelling out, so delocalization energy is 0. Moreover, you can see that in the organic we see it that this is my anti-aromatic system. It is anti-aromatic because it is cyclic, it is planar, and it is following the 4n pi electron rule. Right, so cyclic, planar, conjugation is there and is having the 4n pi electrons are there, so that makes it to be anti-aromatic, and anti-aromatic they are unstable in the nature because of the delocalization energy between them, it is 0 only. So if directly you consider this way, then also the same answer you will be getting, and the proof for the delocalization energy is there in front of you. Okay, so that makes the option A to be the right answer. Got it? Next, this question now, again same paper, so you are seeing from the June 2011 number of questions are there, right? So make sure you do this unit very well. If the question it says, for a certain particle encountering a barrier, the tunneling probability is approximately e raised to the power of minus of 10 of it. If the mass is halved and the width is doubled, the approximate value of the tunneling probability is. We know that the tunneling probability this is equal to e raised to the power of minus of 2 under root of 2m times the v minus of e upon the h cut into the L of it. Now what they have done is, its value is given, it is e raised to the power of minus of 10. Now a new mass, which is suppose m dash, it is half of the previous one, and the length that you have, it is twice of the previous one. So now the new tunneling probability, it's gonna be e raised to the power of minus of the 2 under root of 2 times the m dash into the v minus e upon the h cut into the L dash of it. So now this you can substitute, because the new values in terms of the previous ones we can write it 2 times the m upon the 2 into v minus e into the, now L dash was equal to the 2 times the L, so 2L it will come upon the H cut it was there, right? So now this 2 that you are having, it will be coming in the under root of it, so that will become as 4 e raised to the power of minus of 2 into the 2m into the v minus of the e upon the 2 into the 4. Now L it was present outside only, and here in the denominator h cut will be there. So with this 2 and 4, 2 it will be left, right? So we are getting the value, that is e raised to the power of minus of the 2 under root of 2m times the v minus e upon the h cut into the 2 and into the L we are getting. So this is the value we are getting. So this you can rearrange a bit. That will become e raised to the power of minus of 2 root of the 2m times into the v minus of the e upon the h cut into the L into the root of 2. Like this we can write this value, right? Now this value we have already been given, that is e raised to the power of minus of 10 into the under root of 2. So this new value it will become, right? Because this was already given to us. So the new tunneling probability is e raised to the power of minus of 10 into the under root of 2. So that makes minus of the 10 into the root 2. Option B, it becomes the right answer in this. Right? Next, this question now. Again, June 2011 only. An operator A is defined as minus of d by dx. The operator A is minus of d by dx plus of the x. Which of the following statement is true? So regarding the Hermitian and the anti-Hermitian properties is there. So if A dagger it is equal to A, then the particular operator it is called to be the Hermitian. It is called as Hermitian. If the A dagger it is equal to minus of A, then this particular operator is my anti-Hermitian. Anti-Hermitian. If my A dagger it is not equal to the A, then it is called as non-Hermitian. Okay. So now these properties, these values we need to find for this given A operator. So I'll be taking the dagger of it. So that is gonna be minus of d by dx plus of the x, its dagger. So on opening this, it will become minus of the d by dx, its dagger we have to take it, plus of the x, dagger of it, right? So now it will become minus and the d by dx dagger, right, plus of the x, dagger of it. Now we know this thing that the dagger of d by dx dagger it is minus of d by dx and the dagger of the x it is x only. This properties we know it and that is what we are gonna use. So it will become minus of d by dx plus of the x. So we are getting d by dx. So we are getting here is d by dx plus of the x we are getting, right? So you can see we are not getting the same operator, we are not getting in this, right? So that makes A is not the Hermitian. A is not the Hermitian, right? So based upon this, the first statement that it is saying A is a Hermitian, it becomes to be the incorrect, right? Next it is saying A dagger, it is an anti-Hermitian operator. A dagger is anti-Hermitian. So is it so? No, it is not because negative sign is not coming in front of it. So A dagger is not equal to the minus of A. So again the incorrect. Next it is saying both of the A into the A dagger and A dagger into the A are Hermitian. So let's check this one. So A into the A dagger, again the dagger of it. Now I know this property that AB dagger, this is equal to B dagger into the A dagger of it. Okay, this property we will be using. Now instead of the B it is A dagger, so it will become A dagger's dagger into the A dagger of it. So it will become A into the A dagger. So same you are getting. So that means it is your Hermitian. It is the Hermitian. Now the other one it was A dagger into the A, right? So it was A dagger into the A. Its dagger if I am taking, so it will become A dagger into the A dagger's dagger. That will be equal to A dagger into the A only. So same operator we are getting. So again it is coming out to be the Hermitian one. So this statement it is the true one, we can say that these two, both of this they are the Hermitian only. So option C will be the right answer. Right? D it is saying that A into the A dagger is Hermitian, but A dagger into the A it is anti-Hermitian, again the incorrect one. Okay, next, same paper, June 2011. The question it says a hydrogenic orbital with the radial function of the form which is R alpha, exponential of the minus of beta r, and the phi part in this it is e raised to the or the exponential of minus of the 3 iota into the phi of it, right? So now the wave function of the hydrogen atom, we write it in the terms of the polar coordinates, which is my r, theta and the phi, it consists of two of the parts, the radial part and it consists of the angular part, which is dependent upon the theta and the phi terms. The angular part that you have, it is sine raised to the power of m theta into the cos of L minus of the m theta e raised to the power of iota m phi. So this is my phi part in this, right? So the given phi part, it is exponential of minus of the 3 iota into the phi. Correlating both of this, we get the m value as minus of the 3 in this, right? Based upon this, the options, if I see, first is saying m is 3, it can't be the 1. M is 3, we need to take this into the consideration. Here again C is saying m is 3, again this can't be there. D is saying m is minus of 3, so this also we can take into the consideration. Now the value of the L and the N, we have to find it. So for the L, we use this cos theta term. So in the given, this cos theta value we are going to use. In the given expression of the wave function, no cos theta term it is there. That implies the L minus of the mod of M, this is equal to 0, right? So L minus of the 3, it is 0 because minus of 3 it was there, its mod we have to take it, so it will become L minus of the 3 only. So L value, it comes out to be as 3 in this case, right? So L value is 3 in both these scenarios. L value is 3 only, so that means with the L value we are not able to differentiate between them. We need to find the N value. So for the N part, what you do is find the number of the radial nodes present in this. For that, keep this radial part of the wave function equal to the 0 and find the R value where this particular wave function is gonna be 0, because nodes are the regions where the probability of finding the electrons or the particles, it is 0, right? So for the n, find the radial nodes, radial nodes. So the wave function, it was r is to the power of alpha exponential of the minus of the beta into the r. This value we have to equate to the 0. So based upon this, we get r value equal to be 0. Only then this wave function is gonna be equal to the 0 only, right? So that means the number of the radial nodes in this, it is 0 only. Radial nodes is 0 only because this is this r value equal to the 0, it is your boundary conditions, right? Other than that, the regions that you get where the probability of finding the electrons is the 0, that is the position of the radial nodes. Okay, so n minus L minus 1 is 0, so it will become n minus 3 minus 1, that is 0. Based upon this, n minus 4 is 0, or we can say that n value is 4 in this case. So this is gonna be the answer in this. So n is 4, so that makes the option B to be the correct answer, right? Next, again the same paper, CSIR June 2011. So you can see the frequency of the questions that you are getting, right? It says for the hydrogen molecule, the ground state wave function psi12, it is equal to two of the parts phi12 and the sigma12. Sigma12, where phi it is representing the space part and the sigma it represents the spin part of the wave function. So this is the spin part. Given the condition to us, that is my phi12, this is equal to phi of the 2,1. Phi of the 2,1, which clearly implies that this space part of the wave function, it is symmetric in the nature. It is symmetric in the nature. We want that the total wave function, it should be anti-symmetric. It should be anti-symmetric, that is the space part in this that you are having, it is given to be the symmetric. Space part is symmetric and the spin part that we are left with, that is gonna be anti-symmetric, because when you multiply both of this, you are gonna get the anti-symmetric wave function. Okay, So the spin part is gonna be this anti-symmetric. So we have three of the different conditions where this values you find it. We take the space spin part of it as alpha 1, alpha 2, beta 1, beta 2. We have it. We have the alpha 1, beta 2 plus of the alpha 2, beta 1. And the fourth one, the spin part we have, that is alpha 1 beta 2 minus of the alpha 2 beta 1 of it. Out of this, the first three wave functions that you are having, which is of the spin part, this part it is symmetric in the nature, right? What is meant by this term symmetric? That is, if I change the values of this 1 and 2, if the same result I am getting in that, then that particular wave function is symmetric. Okay. Whereas this part, which is alpha 1 beta 2 minus of the alpha 2 beta 1, this part it is your anti-symmetric in the nature. How I can say that it is anti-symmetric? Interchange the 1 and 2. You are getting alpha 2 beta 1 minus of the alpha 1 beta 2 of it. So rearranging it, we will be getting minus of the alpha 1 beta 2 minus of the alpha 2 beta 1. So this is a negative of the wave function you are getting, which clearly implies it as anti-symmetric, right? So that makes this one, which is with the negative part, option C to be the right answer in this case. I hope the concept it is clear, right? Now moving to our next question. Now moving to our next question we are having, that is this one. Again, the same paper, it says this question we have already done, right? So this was the same question that we have done. Next, this question, so same paper we are having. It says identify which of the following operators is not the Hermitian. That means in this A dagger, it is not equal to A. That is called as the anti-Hermitian or the non-Hermitian. If it is equal to negative, then it is anti-Hermitian. If it is equal to the not equal to the A, then it is non-Hermitian. Okay, so this would be non-Hermitian, or it is A dagger is equal to minus of A, then it will be anti-Hermitian. That means not the property of the Hermitian it will be following. So first one, it is h cut upon the iota d by dx of it. The dagger of it I have to take it. So the first one, it is h cut upon the iota, the dagger of it, into the d by dx of this dagger, right? So now h cut, it is constant, will be coming outside, and the dagger of iota, it is minus of the iota it will become. This will be minus of the iota. Next, d by dx dagger, if I see, d by dx dagger, it is equal to minus of the d by dx. We know this thing. So minus of d by dx. So negative negative will become positive. So it becomes h cut upon the iota d by dx. So again the same operator we are getting. So that means this given one, it is Hermitian in the nature. So the given one, it is Hermitian. Right, so this can't be the answer. Next is iota times the del square by the del of the x square. Iota times the del of by the del of the x square. Del square upon the del of the x square. The dagger of it, it will become iota dagger into the d by dx square, the dagger of it. So this iota dagger, it is minus of the iota. This can be written as d by dx dagger and then the square of it. These properties are there. So it will become minus of the iota. This is minus of the d by dx, the square of it. So it will be coming out to be minus of the iota d square by the d of the x square. So negative sign is coming in front of it. That means it is anti-Hermitian in the nature. It is anti-Hermitian. So not the Hermitian, option B will be the right answer. Right. Next, you can also check d by dx square. Next is d by dx square. the dagger of it, it will be d by dx dagger, the square of it. It is minus of the d by dx, the square of it. So it will be equal to the d square by the d of the x square only. Same operator we are getting. So it is Hermitian. Right? The next, it is x square. So x square dagger, it will be x dagger square of it. X dagger is x only, so the square of it, it will become the x square only. So same operator again, so it is Hermitian. Right? So option B is only the one in which not the Hermitian one we are getting it. Okay, I hope it's clear. Next, this now begins the questions from the CSIR exam of the December 2011. It says that a particle is constrained in a 1D box which is of the length 2a with the potential values, it is infinity. So this box I am having from the minus a to the plus a. This is the 2a length. The potential which is present, x is less than the minus of a and x is greater than the a, it is infinity. So outside it, the potential is infinity and inside it, it is 0. Right? Energy difference we have to find it. So what is the energy for this? We will be getting for a 1D box energy is n square h square upon the 8ma square. Now here it is 2a. So 2a will be kept. So it becomes n square h square upon the 32ma square of it. Right. So now for the energy difference for the n is equal to 3 and n is equal to 2. This we have to find it. So delta E energy for the n equal to 3 minus of the energy which is for the n equal to 2. So this will become 3 square h square upon the 32ma square minus of 2 square into the h square upon the 32ma square. So that becomes 9 minus 4, that is 5h square upon the 32 ma square of it. So this is the energy value we are getting. So that makes option D to be the correct answer. Okay. Next, this from the December 2011 again. For the eigenstates of the hydrogen atom, which of the following relationships between the expectation values of the kinetic energy and the potential energy it holds the true? So the kinetic energy and the potential energy relation is given to us by the Virial theorem. Virial theorem, according to which twice of the kinetic energy is B times the potential energy in it. So what is B in this? It is power of the position that you have. Power of the position. Okay. Now here it is for the hydrogen atom. For the hydrogen atom, the potential energy that we have, it is minus of the Ze square upon the 4 pi epsilon naught into the R of it. So potential we are seeing it is proportional to R raised to the power of minus of 1 of it. So B value is the power of it, that means it is minus of 1. Right? So that implies 2 times the kinetic energy is minus of this potential energy. So this is the relation. This is minus of the potential energy. So this is the answer. 2 times the kinetic energy is minus of the potential. This I can see it is given to us in the option B. So B is gonna be the right answer. Okay. Next, this one. Which of the following is true for the radial part of the hydrogen atom wave function R and L? R over here, where n is the principal quantum number and the nodes associated with them. Okay, so in this, the plot if I see, which is for the R of the R versus the R plot. For the 1s orbital, firstly, if you see the plot, you get it like this. It is R, which is for the 1s. Here the R, which is the distance. The plot we get, that is, goes like this. This type of the plot we get in this. Right? Whereas for the 2s orbital, if I see, for the 2s, we are getting again the plot R of the 2s versus the radial part of it. So again it begins from the peak over there like this, some height it is there, one node you get in this, and the curve it goes like this, negative direction, and then it goes like this. Based upon this, the statement it says the radial part of only s function is non-zero at the origin. So you can see for the s orbitals we are seeing it is non-zero at the origin. So this is my origin over here, and these values they are non-zero, and the number of the nodes in this, if I see, the nodes are n minus 1 only. Here 2 minus 1, that means one node we have got in this. Here also you can see the number of nodes is n minus 1, 1 minus 1, which is 0 only. Right? So it is non-zero at the origin and it has n minus 1 nodes. So option A it becomes to be the right answer. Next statement also you can see it. It is saying radial part is 0 at the origin. Incorrect. All the radial functions have the 0 at the origin. Again the incorrect you are seeing for the s orbital, you are not getting it 0 at the origin. Right. Next, radial part of all the s functions are 0 at the origin. Again the incorrect, and have no nodes. Again this is also the incorrect. So option A will be the right answer for this question. Okay. Next, this question now that says for a non-degenerate perturbation theory for the ground state with the E00 as the zeroth order energy. So we are having E00. This is your zeroth order energy, right? And the E01, E01. This is the first order perturbation that has been applied to it. First order perturbation, and the E naught is the exact. E naught is the exact energy in this, right? So for this, the relationships we have to tell between them. We know that the first order perturbation values that you get, it is either equal to the 0, or this value it is positive, or it is positive. It is never gonna be negative, right? So that means if in the zeroth order energy I'm adding this correction, which is the first order perturbation, to it, if we are adding, which is E01, either it is equal to 0, or this value it is equal, or it is gonna be greater than that. That means from the exact value, this value is always gonna be greater than equal to the exact value of it. So this is gonna be the relationship for this. Okay, so this is your exact energy. The energy that when we will be getting, that is always gonna be greater than equal to the exact energy. So based upon this, the first one it is saying it is always equal to the E naught. Incorrect. Always word it is not the correct. It may or may not be equal to it. Okay. Next, this is it is saying that it is less than the exact value, it is more. So that would have been possible if this value it would have got been to be the negative, and that negative for the first order perturbation is not possible. For the second order perturbation, the negative value it is possible. So this for the first order it becomes to be the incorrect, right? C, it is saying that this sum is greater than equal to the E naught. C value is the C option is the correct one. D, again this is the zeroth order energy and the perturbation is added to the exact value. Again it is the incorrect one. Okay. So next, an excited triplet state wave function of the hydrogen molecule with the electronic configuration which is sigma G1, sigma U1. Sigma G1 and the sigma U1. So the spin value of this, if you consider, it is half plus of the half, which is 1. So multiplicity is 2s plus 1. 2 into the 1 plus 1, that is 3. So this is my triplet state, right? So its corresponding space part we have to tell them. So here it's space part we have to tell them. So for the triplet state, the spin part, if you see, this spin part, it's gonna be alpha 1, alpha 2, we have the beta 1, beta 2, and we have the alpha 1, beta 2, plus of the beta 1 alpha 2. So these are the combinations where the alpha and the beta, it represents the direction of the spins. Alpha is in the clockwise, that we represent it like with the plus arrows, and beta is in the anti-clockwise direction, that you denoted with the down sign. So the corresponding value of the spin, if you see, we will be getting over here. So this value will be 1 in this case. This value is gonna be minus of the 1 over here, because minus of half, that becomes to be the minus of 1, right? Now here it is positive, negative, negative, and the positive. So it will become plus half, minus of the half, minus of the half, plus of the half. That comes out to be 0. All these three spin parts that you are having, these are your symmetric one. These are the correspondingly spin parts which is possible, and all these three are the symmetric, which implies to make the overall wave function to be anti-symmetric, the space part, it should be anti-symmetric. For total psi to be anti-symmetric, the space part, it should be anti-symmetric. It should be anti-symmetric. Right, that means this wave function, it will be possible for the spin part, that is sigma g1, sigma u2 minus of the sigma u1 and the sigma g2. So this is gonna be there, which is your anti-symmetric wave function, space part of your wave function. Okay, so from the options, the one with the negative sign, this only it is given. So option C, it becomes to be the right answer. Okay, next, for any operator A and its adjoint, the incorrect statement is, okay, first it is A and the A dagger is Hermitian. So let's check this. A dagger, it will be A dagger's dagger into the A dagger, because AB dagger is B dagger into the A dagger only. So it will be A into the A dagger. So again the same operator we are getting. So it is your Hermitian only. Right. So this statement, it is my true one. Next, A plus of the A dagger, A plus of the A dagger, sorry, A into the A dagger plus of the A dagger into the A, it is Hermitian. Again, let's check it. So it will be A daggers, dagger it will be there, plus of the A dagger into the A, the dagger of it. So it can be opened as A dagger's dagger into the A dagger plus of the A dagger into the A dagger's dagger. Right, so it will be equal to A into the A dagger plus of the A dagger into the A. So same operator you are getting, so that means it is your Hermitian only. So this statement that it is given to be the Hermitian, this is also my true one. Right, next it says A plus of the A dagger is Hermitian, so it will be equal to A dagger plus of the A dagger's dagger, so that will be equal to A dagger plus of the A. Right, so same operator we are getting, so that means again it is your Hermitian only. So that means this statement is also my correct one. Next, it is A minus of the A dagger is Hermitian. So it will be A dagger minus of the A dagger's dagger. So it will be equal to A dagger minus of the A, right? So this can be rearranged as minus of the A minus of the A dagger. So this was the initial operator. Now here a negative sign is coming in front of it. That means it is your anti-Hermitian in the nature. It is anti-Hermitian in the nature and not the Hermitian one. Right? So this statement that is given to us, that it is Hermitian, this is my false statement. So incorrect only, the option D will be the right answer. Okay. Next we are having, that is this question. So this is from the CSIR exam of the June 2012. The question, it says, for the hydrogen-like atoms with the nuclear charge Z, the energy of the orbital with the principal quantum number n, it follows the relationship. So for the hydrogen-like atoms, we know that energy, it is minus of 13.6 into the z square upon the n square in the units of electron volt, or it is equal to minus of the 0.5 into the z square upon the n square in the units of atomic unit, right? So we are seeing that energy value, it is proportional to minus of the z square upon the n square of it. So this is gonna be the answer. So based upon this options, if you see, first is n square z square, incorrect. Second, minus of z square upon the n, incorrect. Z square upon n square we want. Here it is z by n, again incorrect. Minus of z square upon the n square. Option D will be the right answer. Okay. Next, again the same paper only. The question, it says the average value of the radius in the 1s or state of the hydrogen atom is, where A0 is the Bohr's radius. Okay, so the average value of the R, this is gonna be equal to, in the bracket notation I am writing it, psi into the this operator which is of the R into the psi and the ket notation that we have kept it. So this is equivalent to integration of psi star into the psi into the psi into the d tau of it. For this hydrogen like atoms, d tau value we talk in terms of the polar coordinates. So r, theta and phi terms are included. D tau value, it is r square dr sine theta d theta sine theta d theta d phi, right? Limits for the r lies between 0 to infinity, theta lies between 0 to pi, and the phi lie in between 0 to 2 pi. Okay, so now the psi value that you have, this is for the 1s orbital. So the wave function for this, it is equal to 1 by the root of pi into the a0 raised to the power of 3 by 2 e raised to the power of minus of r upon the a naught of it. So this psi value, r value and this d tau value, just we have to substitute in this and find the value of the r. We already generally learn this value only for the 1s orbital. The r value, it comes out to be 3 by 2 a naught of it. So it is 1.5 a naught. Based upon this, option B becomes the right answer. Okay. Next, from the same paper, CSIR June 2012, the probability of finding a particle in the 1D box of the length L in the region between L by 4 and 3L by 4. N value is 1. For 1D box, the wave function, it is root of 2 by L into the sine of n pi x upon the L of it. Right. N value here, it is 1. So wave function, it is root of 2 by L into the sine of pi x upon the L of it. Right. Now the probability that we find it out, it is integration of psi star into the psi into the dx of it for a 1D box. Limits are from L by 4 to 3L by 4. So it will be equal to root of 2 by L sine pi x upon the L of it. This conjugate we are taking into the root of 2 by L sine of the pi x upon the L integration dx, limits L by 4 to 3L by 4. So this 2 by L, it will be coming out, and this integration will be for from L by 4 to 3L by 4 for the sine square pi x upon the L of it into the dx. So this integration value we have to find it out now. So let's do. We know that cos 2x, it is equal to cos square x minus of the sine square x, or we know this thing also, that sine square x plus of the cos square x, it is equal to unity. So this substitution in terms of the sine and the cos, we can make it. So cos 2x will be equal to 2 cos square x minus of the 1 or it is 1 minus the 2 times the sine square x. So this relationship we are gonna use now. From this you get the sine square x value, that will be 1 minus cos of the 2x upon the 2. So this value we are getting. Okay, so now use this relation in your previous integration. So that will become from the L by 4 to 3L by 4. Outside it 2 by L it is there. Here it will be 1 minus cos of the 2 pi x upon the L, and here 1 by 2 was there, that I am taking it outside. Okay, so this 2 and this 2 will get cancelled. So we will be getting the integration of L by 4 to 3L by 4. Here the 1 by L it is there. 1 minus cos of the 2 pi x upon the L into the dx of it. Here also this value will be there. So on solving this we get the value as x minus sine of the 2 pi x upon the L upon the derivative part of this cos of 2 pi x, and this 2 pi x by the L. So it will be 2 pi by the L. Limits are from L by 4 to 3L by 4. Here 1 by L it was there. So it will be 1 by L into 3L by 4 minus of the L by 4, this minus of this L upon the 2 pi. I am taking it like this, substituting the limits in the sine functions. Sine of the 2 pi into the 3L by the 4 upon the L minus of sine of 2 pi L by the 4 upon the L. So here we are seeing that this L and L in the both these cases it will be cancelled out, and this will become 2. Here also it will become 2. Here it will be coming like this. It will be 1 by L into the 2L by the 4 minus of sine of here 2 by the L upon the 2 pi it was there, minus of L upon the 2 pi sine of 3 pi by the 2 minus of the sine pi by 2. So now substitute these values of the sine. We will be getting that here 1 by L into 1 by the 2 into the L minus of L upon the 2 pi. Now sine 3 pi by 2 is minus of 1 and sine 90 is 1. So this becomes minus of 2 over here. This L term it will get cancelled from both. So it becomes 1 by 2 minus of 1 by 2 pi into the 2 of it. Here minus of 2 it was there. So 2 and 2 it gets cancelled out. It becomes 1 by 2 plus 1 by pi. So this is gonna be the probability in this region. So 1 by 2 plus 1 by pi, option B, it becomes the correct answer. Okay, so the complete derivation part of this I have shown you. Next, this one now, CSIR June 2012 only. A particle in a 3-dimensional cubic box of length, it has the energy which is 14 h square upon the 8 ml square. So 3D box, energy value it is nx square plus of the ny square plus of the nz square into the h square upon the 8 ml square of it. This value it is equal to 14 h square upon the 8 ml square. So nx square plus the ny square plus of the nz square, it is coming out to be 14. Right. So now what could be the possible values of this nx and the ny, so that we can get the degenerate energy levels, and the corresponding energy to that level it is gonna be 14. Okay, so if I keep nx to be 1 square, this to be 2 square, and this to be 3 square. So 9 plus 4 is 13, 13 plus 1 will be 14. So 1, 2, 3 is the possible values of this nx, ny and the nz. So nx, ny, nz value is 1, 2, 3, or we can have the level which is 1, 3, 2. This also is gonna have the same energy. Next 2, 1, 3 or the 2, 3, 1. These also will have the same energy. Next 3, 1, 2 and the 3, 2, 1. All of these levels, they are gonna have the same energy value, which is of the 14 h square upon the 8 ml square. So all these levels, they are called as the degenerate energy levels. These are my degenerate, and degeneracy value is 6, because these are the 6 levels which are having the same energy, right? So based upon this, the correct answer is the option C. Okay. Next, this question again CSIR June 2012. The questions, 3 of the statements about the perturbation theory has been given to us. It's first is second order perturbation correction to the ground state energy is always negative. This statement is the true one, because this correction in the energy of the second order we have seen. Here you apply this perturbation, this delta H, it's a square you put it, and in the denominator for the ground state, from the ground state energy you subtract the energy of the higher states. This denominator value, it comes out to be negative, no matter whether the perturbation is positive or the negative, right? So A is my correct statement. Next, sum of the zeroth order and the first order correction to the ground state energy is always greater than that of the exact energy. This word always is incorrect over here. It may or may not be. This, we have seen it in this class only. We have seen a similar type of question there the relationship was asked to us, but now in the form of the statement they have given to us. Let me just show you that question. So where it was, let's just see where it goes. There the zeroth order energy we were having, and in that the energy, it was perturbation, it was added. This was the one. So you see here, it is greater than equal to, because first order perturbation value that you are having, it could be positive or it could be zero value, it is possible. So energy is gonna be greater than this. It's not always, it may be equal to it or it can be greater than this. So this word always is incorrect over here, right? Next, sum of the zeroth order and the first order correction to the ground state is less than that of the exact state energy. Again the incorrect, because the first order corrections that you have, it is always 0 or it is positive. So it is gonna either be equal to the exact energy or greater than this, never less than the exact energy it is possible. So only A is the correct statement. So the option A, it becomes the right answer. Okay. Next, CSIR June 2012 again. Using the Huckel molecular orbital theory, orbital approximation, the roots of the secular equation for the ethene. So ethene is this one, CH2, CH2, right? So for this, the determinant that we write, it's gonna look like this. It is C11, C12, C21, C22. This we equated to the 0, right? This C value, it is nothing. It is H11 minus of the ES11 of it. Here it will be H12 minus of the ES12. Here it is H22 minus of the ES22 of it. Here it is H21 minus of the ES21 of it. Right. Now this energies, which is of the HII, that means both these II values, that means they are the same. This value is equal to the alpha. Okay, and the values of the Hij, if there is direct bonding, then it is given the value of the beta, and if there is no direct bonding, then this value is 0. So this is if direct bond is there, direct bond is present between the carbon atoms, and 0 if no bonding, if no bonding. Now here two of these are only there, and rest about the SII, this value is 1, and Sij, this overlap is 0. Okay, so now substitute this in this given circular determinant that we have formed it. So carbon 1, CH2, double bond CH2, this is carbon 1 and this is my carbon 2. So H11 direct bonding is there, so it will be alpha minus of the ES11. S11 is 1 only because both these components they are the same. Here it's gonna be beta, and here again beta value. Here also this alpha minus E. This is equal to the 0. Divide all of this with the beta value. So it will become alpha minus E upon the beta. Here the 1 alpha minus E upon the beta. This is equal to 0. Next, let this alpha minus E by the beta value, it is equal to the x. So determinant it will become x1 This is equal to 0. So solve this. Here diagonally you have to go and subtract these values. X square minus of the 1 it is 0. So we are saying that x value it is plus minus of the 1 over here. Right. So based upon this, the energy values, if I see alpha minus E upon the beta, it is either plus 1 or it is alpha minus E upon the beta, it is minus of 1. So this comes alpha minus E is equal to the beta, or alpha minus beta is the energy. Right. And this case alpha minus E is equal to minus of beta, or energy value is alpha plus of the beta. So the two roots that we are getting, it is alpha minus beta and the alpha plus beta of it. So this is gonna be the roots. So alpha minus beta and the alpha plus beta, option C, it becomes to be the right answer in this. I hope it's clear, right? The next one we are having, that is this question now. It says for the hydrogen molecule in the excited state. So let's firstly find what is the state. It is singlet or it is the triplet state. So it's already given that it is your triplet state, so no need to find, because 1 electrons are there. Spin value you can find it out. It is half plus of the half, that is 1. So 2s plus 1 is again 3 only. Right, so triplet state it is there. With the spin part which is having the ms value equal to 0 is proportional to. Okay, so in this triplet state we know the 3 of the spin parts you have which are symmetric. Now all of these 3 they have the different spin values are different for them. So we have the alpha 1, alpha 2, which represents both of these are in the clockwise, that is in the above direction. For this the total spin value which is ms, if you find it out, it is plus 1 in this. Right, next it is alpha beta 1 or the alpha 1 beta 2 plus of the alpha 2 beta 1, and the third part we have it is beta 1 beta 2. So beta 1 beta 2 means both are in the downward direction. Spin value will be minus half, that is minus of 1. Okay, whereas this part it is representing one in the clockwise, other in the anti, again the above and the downwards. So it will become plus of the half, minus of the half, plus of the half, minus of the half. Again it is gonna be, it is now 0 value. So we need the spin part to be ms to be 0 in this. That is possible if the spin part is this one. Right. So alpha 1 beta 2 plus of the beta 1 alpha 2, that is option D, it becomes the right answer. Okay. Next, this one. If A and B they are the not non-commuting Hermitian operators. So A and B are the Hermitian operators, which means A dagger will be A and B dagger will be B only, because these are Hermitian operators. All the eigenvalues of the operator which is given by the commutator of these two operators. So the commutator of these two operators, it is gonna be AB minus of the BA, which implies the difference between them. That is, firstly the B operator is applied upon some wave function, then this A, and B minus of the A, that is A operator is applied first and then this B operator. If they are commuting with the one another, then this value should come out to be 0. Okay. So based upon this we talk about the eigenvalues. The eigenvalues, if we get the Hermitian operator, if we have the Hermitian operator, the eigenvalues corresponding to the Hermitian operators, they have the real eigenvalues, whereas the anti-Hermitian operators that we have, anti-Hermitian operators. For them, the eigenvalues, they are imaginary. These are imaginary. So now what I'll be seeing is, I'll be seeing that whether this commutator operator which we are having, which is AB minus of BA, it's gonna be Hermitian or it's gonna be anti-Hermitian. Based upon that, its eigenvalue will be decided. So let's do. So to find whether it's Hermitian or not, I'll be taking the dagger of this commutator operator, which is equal to AB minus of the BA, the dagger of it. So it will be equal to AB dagger minus of this BA dagger, right? So now I know a property AB dagger is B dagger into the A dagger minus of this will be A dagger into the B dagger. Now B dagger is B only, A dagger is A because these are individually Hermitian operators. It minus of AB. So the initial operator, it was the AB minus of BA. Now I am getting is BA minus of the AB. So I can write it in this form. It is AB minus of the BA only. In this form we can write it. So you can see the commutator operator we are getting with the negative sign, which implies it is anti-Hermitian. Anti-Hermitian. So we can say that commutator of two Hermitian operators, commutator of the two Hermitian operators is anti-Hermitian, and Hermitian operators is anti-Hermitian, anti-Hermitian, that is its eigenvalue is imaginary. So imaginary eigenvalues we are gonna get, right? So based upon this, the option C will be the right answer. Okay, next this question now. So from December exam of the year 2012, the commutator of this x and the px square, x and the px square, we know this is only true for the position and the momentum operators only. Position and the momentum operators only. We have this thing that if you take the commutator of x and the px raised to the power of n, this value it is n px raised to the power of n minus 1 into the iota h cut. Okay, similarly if you talk about px raised to the power of n and the x value, this is gonna be minus of the iota h cut into the n px raised to the power of n minus 1 of it. Okay, in the similar manner, the commutator of this px and the x raised to the power of n, if you have, this is equal to n x raised to the power of n minus 1 into minus of the iota h cut. Okay, and for the x raised to the power of n and the px, this value is n x raised to the power of n minus 1 into the iota h cut. This value we have it. So now based upon these general formulas that I have written, so this is, you can say, number 1, this was number 2, number 3, and this was the fourth one. So we are gonna use this and find the commutator of x and the px square. So x px square, it will be 2p x raised to the power of 2 minus of 1, which is 1 only, now into the iota h cut. This value it will be there. Okay, so 2 times the iota h cut into the px of it. So this is gonna be the answer. So 2 iota h cut into the px, option D, it becomes the right answer. Okay, next again CSIR December 2012, combining two of the real wave functions phi1 and phi2, the following functions are constructed. So two of the real wave functions, which was phi1 and phi2, they took and formed 4 of the different new wave functions, which is a, b, c and the d. So the correct statement will be, so in the statements you see which of the following it is representing that they are in the same state. That means their probability values are the same, because wave function itself does not give us any information about them. It is their square of it, that is about the probability of finding the particles, this wave function can tell us, right? So the A function it is given, A wave function is phi 1 plus the phi 2, the B it is phi 1 plus the iota times the phi 2, C value it is phi 1 minus of the iota times the phi 2, and the D value it is iota times the phi 1 plus of the phi 2 of it. So if I find the probability of this A and the A star, its d tau it will be there. So this value it's gonna be phi 1 plus phi 2 into the phi 1 plus phi 2 into the d tau of it. So this was in the form of conjugate we were having, but there is no iota terms included. So it will be equal to integration of phi 1 plus the phi 2, its square into the d tau of it. Like this we can say it, right? Similarly, if I talk about this d wave function which is given, d into the d star, integration of it, it will be into the d tau, or we can say it is d tau into d star into the d. It will be integration of iota times the phi 1 plus phi 2. Now its conjugate we need it, and into the iota times the phi 1 plus of the phi 2 of it into the d tau. So this will become now iota conjugate, it becomes minus of the iota into the phi 1 plus of the phi 2 into the iota times the phi 1 plus of the phi 2 into the d tau of it, right? Now this becomes the iota square minus of the iota square. So this is phi 1 plus the phi 2 into the phi 1 plus of the phi 2 into the d tau, right? Now iota square it is minus of the 1, iota square is minus of the 1. So this you substitute, you will be getting phi 1 plus of the phi 2 into the phi 1 plus of the phi 2 times the d tau. So this value is coming out to be the same, which is phi 1 plus phi 2 times the its square into the d tau, right? So you are seeing for the A and the D, we are getting the same probabilities we are getting. So which means A and D are representing the same states, right? Similarly for the rest also, B and C, similar way you have to proceed it. You will be seeing no same states you will be getting in them. So it will be A and D, it represents the same states. Option C will be the right answer. Okay. Next, again December 2012. The trial wave function is expanded. So trial wave function it is given, it is C1 phi 1 plus the C2 phi 2 of it. The matrix elements of the Hamiltonian it is phi 1 H phi 1 is 0. That means it is the value of the H11. Next it is phi 1 H phi 2. This value is 2. So this is not 20, it is 2.0. So a decimal is missing. So this value is of the H12, right? Next H21, that is phi 2 H and the phi 1. This value is also equal to the 2 only. So this is the value of the H21. Okay. Similarly, the next we have been given, that is of the phi 2H and the phi 2. This value is equal to 3. So this is the value of the H22. Okay, and the approximate ground state energy of the system we have to find from the linear variation principles. Okay, so that means this function it can be represented in the form of the matrix, that is C11, C12, C21 and the C22 it will be there. So this will be equal to H11 minus of the, or let's go on the next slide only, and the values it will become, that is your H11 minus of the ES 11 of it, H12 minus of the ES 12 of it, and here it will be H21 minus of the ES 2 1 of it, H22 minus of the ES 22 of it, this value is equal to the 0. Right. Now H11, H12, these values are given. For the S11, SII components that we have, it is unity, and the Sij components we know it is 0. We have to assume it. So now H11 value is given, which is 0. So this will become 0 minus of the E. And next H12 and 21 is 2. So it will become 2 over here, and here also it is 2. H22 value, it is given us to be 3 over here. So it will become 3 minus of the E. This is equal to 0. So solve this matrix now. Cross multiply this. So minus of the E into the 3 minus of E minus of the 4. This is equal to 0. Right. So just open this out now. It will become minus of the 3E plus of the E square minus of the 4 is 0, or we can say E square minus of the 3E minus of the 4 is 0. To find the roots, it can be written as E square minus of the 4E plus of the E minus of the 4, that is equal to 0. From this E will come out, E minus of the 4 plus of the 1 into the E minus 4 is equal to 0. So energy values, it will be E plus of the 1, E minus of the 4, it is 0. So we can say that the roots that we are getting, E plus 1 is 0, that implies energy will be minus of 1, and the other one was E minus of 4 was 0, so energy was 4 in this. Now we have to find the energy of the ground state, right? So ground state means the lowest possible value, so this will be the energy that will be of the ground state, right? So it is minus of 1. Option A, it becomes the right answer. Okay. Next, this question now. One molecular orbital of a polar molecule. So polar molecule means the MOT they have taken. It has the form which is Ca psi A. So the wave function is Ca psi A plus of the Cb psi b of it, where psi A and psi b are the normalized atomic orbitals centered on the atoms A and the B. So here respectively, the electron in this orbital is found on the atom B with the probability 90%. So probability of finding the electrons on the B. So Pb value, it is given to be 90%. Okay, next is neglecting the overlap. That means the S value is taken to be 0 between the psi A and the psi B, the possible set of the Ca and the Cb. So probability of B, it is gonna be 90%, which is 0.9. This probability of B, it is nothing, it is the Cb square only, which is equal to 0.9. From this Cb value, if you find it out, it is gonna be root of this, which comes out to be as 0.95. Right. Now the total probability of the finding these electrons, it is gonna be unity only. So it will be Pa plus of the Pb, it is 100%, you can say, or we can say probability of finding the A, it is 100 minus the probability of finding on the B, which is 100% minus of the 90%, which is 10%, right? So probability on A, it is 0.1 only. Similar to PB, Ca square, it will be equal to 0.1. So Ca comes out to be root of the 0.1, which is equal to 0.32. Okay, so Ca we have got, and the Cb value. First it's saying Ca is 0.95, incorrect. Ca is 0.1, again the incorrect. Ca is minus of the 0.95, incorrect. Cb is 0.95, Ca is 0.32. Option D becomes the right answer. Okay, next this question now. Again December 2012. It says suppose the ground stationary states of the harmonic oscillator with the force constant k, it is given, which is psi naught is equal to exponential of the minus of the ax square. Then the a value should depend upon the k as. So relationship between this a and k we have to tell them, right? So for the simple harmonic oscillator, we know that the wave function psi naught that you have, it is the given one and we are having it is exponential of the minus of the ax square, right? And the one which we obtained from the derivation of it, so that is for the SHO, the wave function psi naught, it is proportional to e raised to the power of minus of the beta x square. That means this a value, it is nothing but your beta only. Now relationship of this beta with respect to the force constant, I have to just see it. So in the derivation part of it, that is from our Schrodinger wave equation. Schrodinger wave equation, we know that h psi is equal to the e psi of it. Now this h, it is sum of kinetic and the potential energies on rearrangement. The final equations we get, which is d square, considering to be in the one dimensions only, so d square by the d of the x square times the psi plus of the 2m upon the h cut square into the e minus of the v times the psi. This value, it is equal to 0, right? So now for the SHO, potential energy is half of the kx square, where k is your force constant. K is the force constant, right? So this d square psi by the d of the x square plus of the 2m upon the h cut square into the e minus of the v, which is half of the kx square times the psi, this is equal to 0, right? Now further open these brackets, so we get d square psi upon the d of the x square plus of the 2m upon the h cut square into the e, this value plus of the, next we get minus of the 2m upon the minus of 2m into the h cut square, 2m upon the h cut square into the half k square, half of the kx square, right? So this 2 and 2, it gets cancelled, so minus of the mkx square upon the h cut square times the psi, this is equal to 0. So this is what we get. Now in this, the substitutions we make it, we substitute the value that as alpha, which is 2me upon the h cut square, and the beta we substituted as root of the mk upon the h cut of it. So this substitutions we make it. So from here we are seeing that beta value, it is proportional to root of the k over here, right? So this is what you will be needing over here, because beta x square, relationship of this beta with the k, we have to see it. So beta is proportional to root of the k value, right? So a will be also proportional to k raised to the power of 1 by 2. So that makes option C to be the right answer. Okay, so through the complete derivation part that we include in the deriving the wave function part of it from the Schrodinger equation, there the substitution that we make, that too I have shown you. Okay, next this question now, again CSR exam of the December 2012. It says the energy of the harmonic oscillator. So SHO again is half of the h cut into the omega. According to the virial theorem, the average kinetic energy and the potential energies is. So energy value, it is half of the h cut omega. The according to the virial theorem, twice of the kinetic energy, it is B times the potential energy. B is the power of the positions that we have. So twice of the kinetic energy. Now B value I have to find it. So in the SHO, the potential energy is half of the kx square of it. So B value is 2 in this case. So we can say that twice of the kinetic energy, it is twice of this potential energy. So we are seeing that kinetic energy is equal to the potential energy for the SHO. So now the total energy will be the sum of E total. It is sum of the kinetic energy plus the potential energy, which is this T plus of the V. Now 2 times the T we can write it. This is equal to the E total. So kinetic energy, it's gonna be E total upon the 2 of it. So 1 by 2 of the this value it is given, which is half of the h cut into the omega, half of the h cut into the omega. So kinetic energy is 1 by 4 h cut into the omega. Similarly, the potential energy is also gonna be 1 by 4 into the h cut omega, right? So both are this same only, 1 by 4 into the h cut omega. These values are given. Option A becomes the right answer. Okay. Next, again, CSR December now 2012. The question, it says the energy of the hydrogen atom in a state is this much, which is minus of the HCRH upon the 25, minus of the HCRH upon the 25. The degeneracy in this we have to find it. So the general formula for the energy, we know it is minus of the Hc into the RH into the Z square upon the N square of it. Now for the hydrogen atom, the Z value is 1 and the N we are considering it to be the 1 only. So the energy value, it becomes minus of the, sorry, not the 1, N value, because N square will be giving us the degeneracy. So it becomes Hc into the RH upon the N square. So this now is equal to the given one, which is minus of the HCRH upon the 25. From correlating both of this, we get that my N square value, it is equal to 25, right? So this N square, it is nothing but your degeneracy only, that is denoted with the G. So degeneracy is 25. That makes the option C to be the correct answer. Okay. Next, again CSIR December of 2012. It says in a many electron atom, the total orbital angular momentum, this is L, and the spin are good quantum numbers instead of the individual L1, L2 and the spin values angular momentum in the presence of. In this, the one, as we go to the many electron systems, in that we consider the LS coupling, or we consider the JJ coupling, we consider it, where the J value we write it as the sum of L plus S to the L minus S, we have to take it. So like this, the couplings we included. Reason being, in the many electron systems, there is gonna be inter-electronic repulsions. Due to that, these couplings we have to take into the consideration. Okay. So answer is A in this. Next, the difference in the energy levels of n and the n is equal to 2 and n is equal to 1 for a particle in the one-dimensional box is 6 units. So energy for the particle in a 1D box, the energy value, it is n square h square upon the 8 ml square. Now the difference between them, it is for the n is equal to 2 and n is equal to 3, it is given. So this energy difference between them, n is 2 and the n is 1, sorry, 2 and the 1. So the energy difference, it will become, that is 2 square h square upon the 8 ml square minus of the h square upon the 8 ml square. So this becomes 3h square upon the 8 ml square of it. So this value is given us to be 6 units, right? So from this we can find the value of h square upon the 8 ml square, right? H square upon the 8 ml square, this was 6 units, so it will become out to be 2 units. So h square upon the 8 ml square is 2 units, right? Now the next, we are asked to find what is the difference in the energy levels of n is equal to 3 and the n is equal to 2 for the above system. So in the same units answer we have to give them for n is equal to 3 and n is equal to 2. So energy, it will become 3 square h square upon the 8 ml square minus of the 2 square h square upon the 8 ml square. So it will become out to be 9 minus 4 into the h square upon the 8 ml square, that is 5h square upon the 8 ml square. This value in the term of units we have got it, that is your 2 units. So answer, it comes out to be as 10 units for it. Okay, so this is the energy difference. So 10 units, option D, it becomes the right answer. Okay, next, this now, June 2013 paper we have began now. The question, it says the wave function psi of a certain system is the linear combination of this wave function. So wave function we write it as C1 phi 1 plus the C2 phi 2 of it. Here we have been given, instead of it, it is 1 by 4 psi 1 plus of the root of 3 by 4 psi 2 of it, where psi 1 and the psi 2, they are the psi 1 and the psi 2 are the energy eigenfunctions with the eigenvalues, which is E1 and E2 respectively. That means corresponding to the psi 1, the energy we will be getting, that is E1, and corresponding to this, the energy it will be E2. What is the probability that the system it has the energy, as energy observed, will be equal to the E1 in this? Okay, so here firstly let us check that this given wave function is normalized or not. For that, C1 square plus C2 square, it should come out to be unity. So C1 value is 1 by 4, the square of it, plus of the root of 3 by 4, the square of it, it is coming out to be 1 by 4 plus of the 3 by 4, that is equal to unity. So system is normalized over here. Okay, now the probability of getting the energy E1, this is nothing, probability of getting energy E1, it is equal to the C1 square only, right? And C1 we have seen that it is 1 by under root of 1 by 4, so it's a square only, it will be there, that comes out to be as 1 by 4. So this is the probability of getting the energy on as the E1. So 1 by 4, option C becomes the right answer. Okay, next, for a particle in a box, an approximate wave function is given by x L by 2 minus of the x into the L minus of the x. So this is given as the trial wave function. Now the average value of the energy for such state it is gonna be. Okay, so firstly let us see this wave function which is given to us, it is corresponding to which state. So based upon that, the energy values we will be finding it. So here firstly you find the nodes in it. So for that, equate this wave function equal to the 0. So x into L by 2 minus x into the L minus of the x is equal to 0. So from this we get x is equal to 0 or x is equal to L by 2, and we are getting x is equal to the L. So these three values of the x we have got it. So x is 0, x is L by 2, and x is L over here. So in these three conditions, the wave function value it will be 0, right? So here if I see this x is 0 and x is L, these both are the boundary conditions. Boundary conditions. So these are not counted into the nodes. This is also the boundary conditions. Only this is the position of the node that you are gonna get, right? So that means nodes number it will be 1 only. Now n value if I find it, n minus 1 is 1 only, that is equal to the number of the nodes. So n value in this we get as equal to the 2. That means the trial wave function which is given to us, it is corresponding to the second state. Okay, so now for a particle in the 1D box, the energy value for the second state we have, that is 2 square h square upon the 8 ml square, or it is 4h square upon the 8 ml square of it. So 1 by 2 it will become. So that means it is h square upon the 2 ml square of it. So this is the energy of the exact state, right? Exact one. So the trial wave function energy that you have, energy for the trial wave function is always greater than or it is equal to the exact one, right? So that means trial wave function energy will be greater than h square upon the 2 ml square, that is given to us in the option B over here. It's not equal to, it's always greater than this. So based upon this, option B it becomes the right answer. Okay, next, this question now, again June 2013, the hydrogenic orbital which is of the form of the radial function which is r square, alpha 1 minus of the r, alpha 2 minus of the r, exponential of the minus of the beta r of it, where a1, a2 and the b are the constants, may be identified as. So different orbitals have been given to us. We have to find it out which of the given orbital is corresponding to the given radial wave function. So for that what you do is, from the given radial wave function, firstly find the number of radial nodes in it. Radial nodes, firstly we find it. For that you keep the given wave function equal to the 0. That is alpha 1 minus r, alpha 2 minus of the r, exponential of the minus of the beta r, it is equated to the 0. So we will be getting the radial wave function equal to 0 if r is equal to alpha 1 or r is equal to the alpha 2. Rest are the boundary conditions. So these two scenarios are there which is gonna correspond to the radial nodes. So these are the position of the radial nodes. So the number we have got it as 2 radial nodes we have gotten this. Right. So now in the given orbitals, we have to see the one which is gonna have the 2 radial nodes, that is gonna be the orbital for which the wave function has been given to us. So first orbital, it is 3D. So firstly is 3D orbital. Number of radial nodes is n minus L minus 1. Now these L values, if you see, for the different orbitals, your S, P, D and the F, L values are 0, 1, 2 and the 3. So now in the 3D, N value it is 3, L value we have got, that is 2, minus of the 1, it is 0. So 0 radial nodes we are getting. So this is not gonna be there. Next is 4F. 4F, again n minus L minus 1, it will be 4 minus of the 2 minus of 1, 1 radial node we are getting in this. Right. Next 5D. In the 5D again n minus L minus 1, sorry, here it was n L value, it was 3 over here. So 4 minus 3 minus of 1, again 0 radial nodes we were getting. In the 5D, it will be 5 minus of the 2 minus of 1. So 5 minus 3 is 2. So you can see 2 radial nodes you are getting in this. That implies option C will be the right answer, because these many radial nodes you are getting in the 5D, which are corresponding to the given radial wave function. For the 5F orbital also you can check it. For the 5F, it will be 5 minus of 3 minus of the 1. So it will be 1. Again, it is not equal to the given one. So that means these many radial nodes are not there. So one node was there. So this is also the incorrect one. So option C is the right answer for this. Okay. Next, this question. The operator value which is given as the x, commutator of x and the px, p square of it, and this is commuting with the x, then it is identical to. So the given commutator, operator's commutator, if I see, firstly, like we have seen that x, px, n, this value of commutator is n px raised to the power of n minus 1 into the iota h cut of it. So this is what property we are using. So x will be commuting with 2p into the iota h cut, right? So this will be commuting. So now this constant which is 2 iota h cut, it comes outside the commutator of x, and the p, it will be there then. Now x and p commutator, the value is minus of the iota, it is plus of the iota h cut. So into the 2 iota h cut. So iota it means the iota square, that will be minus of the 2 h cut square. So this is the value of this operator we are getting. Now based upon this, we have to check for the other ones also. So first one, it is given, that is px and the x and the p. This x and the p, firstly we will be solving. It will be iota times the h cut. Now this is commutator with the constant, so it is gonna come out to be a 0, because this is my constant. Commutator with the constant, it is 0 only. Reason being, we will be getting px and the iota h cut. So it can be written as px into the iota h cut minus of the iota h cut into the px of it. Iota h cut, you will be getting px minus of the px only. So that is gonna come out to be 0 only. So this is the reason for that. Okay, so that means this is not the correct one. Next, xp into the x and the p. So b1, it is xp, x and the p. Right, so again it will be iota h cut commuting with the x and the p. So again this is my constant, so it will come out to be 0. So again not the correct one. Next, minus of the p, x square and the p. So minus of the p, x square and the p. Right, so now this value, it will be coming out to be as 2x into the iota h cut of it. Right, this will be, we will be getting this commuting with the p and here this negative sign. So constant value, which is minus of the 2 iota h cut, it comes outside. It will be p and the x. So this comes out to be as minus of iota h cut into the minus of the 2 iota h cut. So this becomes minus minus will be plus. So 2 iota square into the h cut square, that is minus of the 2 h cut square only. So this value we are getting. So you can see the desired one was also minus of the 2 h cut square, and the commutator for this also we have got this same answer. So that means the correct answer is the option C in this case. Right, because this is giving me the exact value of the above one. Okay, next, this for a particle in a box, the value of the x cube when n approaches to the infinity. So n is approaching to infinity. The general formula you have, that is for the x raised to the power of n, it is L raised to the power of n upon the n plus of the 1. So this scenario, this formula we will be using only when the n is approaching to the infinity. This is important condition. Okay, so now for the x cube, it is L cube upon the 3 plus of the 1, that is L cube upon the 4. Okay, so L cube upon the 4, option C becomes the right answer. Okay, next, identify the Huckel determinant for the cyclobutadiene. Okay, so cyclobutadiene, it looks like this. We have the carbon C1, C2, C3 and the C4 of it. So the wave function for this, it will be C1 5 1 plus the C2 5 2 plus the C3 5 3 plus of the C4 5 4. Now this wave function in the terms of the determinant, if you want to write it, so it will become C11, C12, C13, C14, C21, C22, C23, C24, C31, C32, C33, C34 and then the C41, C42, C43, C44. This determinant you equated to the 0. And this value of the C, it will be equal to, that is my H11 minus of the ES11 of it. It will become next H12 minus of the ES12 of it. H13 minus of the ES13 of it. H14 minus of the ES14 of it. Right. Similarly, the next, it will become H21 minus of the ES21, H22 minus of the ES22 of it, H23 minus of the ES23, H24 minus of the ES24. Next, H31 minus of the ES31, H32 minus of the ES32 of it, H33 minus of the ES33, H34 minus of the ES34, here H44 minus of the ES44, it will be coming H43 minus of the ES43, H42 minus of the ES42, H41 minus of the ES41, 1, right? So this is the determinant. This is equated to 0. Now these values that you have, if you have the HII, the values will be alpha, the HIJ, this value is gonna be 0 or it is gonna be beta. 0 will be there if no direct bond, if there is no direct bond, and beta if direct bond is there. Direct bond is there. Next, the SII value, it is 1 and the SIJ value is 0. Okay, so now these conditions we are gonna use. So this bonding, always remember, it is for the first carbon, second, third and the fourth one. So here we were having H11, so it is alpha minus E, and on this position you were having alpha minus alpha 2 H22, you are having here also alpha minus E. The diagonal elements are gonna be alpha minus E only. Okay, because it is H11, H11, H22, H33 and the H44, and the S44, S33, that is gonna be equal to the unity only. Okay, so this diagonal elements we have written. Now the remaining things will be of the beta concept only. Based upon that, if there is direct bonding is there, then beta, if not it is 0. So between 1 and 2 bonding is there, so beta. Between 1 and 3 no direct bond, so 0. Between 1 and 4 bonding is there, so beta it will come. Okay, between 2 and 1 bonding is there, so beta. Between 2 and 3 bonding is there, so beta. Between 2 and 4 no bonding, so 0. Okay, next between the 1 and 3 no bonding, so 0. Between 2 and 3 bonding is there, so beta. Between 3 and 4 bonding is there, so it will become beta. Okay, next between 4 and 1 bonding is there, 4 and 2 it is not there, 4 and 3 it is there, so beta. So this will be the secular determinant. Okay, so alpha minus E, beta 0 and the beta. So alpha minus E, beta 0 and the beta is there over here. Here it is 0, so incorrect. Alpha minus E, beta 0 and the beta. The first row is correct one. Second one we are getting beta z, alpha minus E, beta and the 0. So we are getting beta, alpha minus E, beta and the 0. Here 0 is not there. So this also becomes the incorrect one, right? Next, alpha minus E, beta 0, beta. The first one is correct. Next, beta, alpha minus E, beta and the 0. This is also correct. The third one, it is 0, beta, alpha minus E and the beta. So 0, beta, alpha minus E and the beta. And the fourth one is beta 0, beta and the alpha minus E. Beta 0, beta and the alpha minus E. Option C is the right answer. I hope it's clear, like how we have done this. Okay, so option C for this is my right answer. Okay, next this question now. It says in the formation of the hydrogen molecule from the two of the hydrogen atoms which are placed at the positions A and B and are separated by a distance which is RAB, a part of the spatial wave function it is given, which is phi A, phi A1, phi A2. That means both these electrons 1 and 2 are centralized on the atom A only, right? And the second is beta, this phi B1 and the phi B2. This also means both these electrons are present upon the B term only. B atom it is present. That means it is representing their ionic character, right? Both these electrons are on the same atom only. So this ionic character it dominates when the R distance that you have it is approaching to the 0. Okay, so the given is, this is the covalent term, incorrect. This is the ionic term and is important as R approaches to the infinity, incorrect. R should approach to the 0. It is covalent and is important, covalent it is not there. It is ionic and is important as RAB approaches to 0. Option D becomes the right answer. Okay, next, December 2013 we have reached the orbital with the two radial and the two angular nodes. So angular nodes it is equal to their n value, L value only. So and the radial nodes it is equal to n minus L minus 1 of it. Okay, so now for the orbitals, L values for the S, P, D and the F, L value is 0, 1, 2 and the 3. So that means that D orbitals only it will be there because they are gonna have the two angular nodes. So based upon this, first one can be eliminated, third one can be eliminated. Answer is gonna be from the B and D only, right? So in the 5D, now the radial nodes, if I see it as n minus L minus 1, 5 minus 2 minus 1, that is equal to 2 only. So you can see we have got the 2 of the radial nodes. So answer is the option B only. D1 you can check it, the number of radial nodes, it will be 8 minus of the 2 minus of the 1, that is 5 radial nodes you will be getting. So this is large number of radial nodes we are getting. So option B is the only right answer. Okay. Next, this question now. It says consider the two-dimensional harmonic oscillator with the potential energy values as this. If the psi n x and psi n y are the eigen solutions and the energy values are the eigenvalues of the harmonic oscillator problem in the x and the y direction with the potentials half kx square plus of the half of the ky square respectively, the wave function and the eigenvalues uh, of the above two-dimensional simple harmonic oscillator is gonna be. So very easy one, just instead of the one dimension, now the two dimension SHO they are talking, right? We just remember this, that wave functions they are multiplicative in nature, they are multiplicative in nature, and the energy values these are additive in the nature, these are additive in the nature. So based upon this, the total wave function which is of the nx and the ny, this is gonna be wave function along the nx into the wave function along the ny, and the energy along this nx ny, it is additive, so it will be energy nx plus of the energy ny. So this will be the values. So based upon this, the options, let us see. It is saying wave function is additive, incorrect. Wave function is multiplicative, energy is also multiplicative, incorrect. Wave function is multiplicative, energy is additive. Option C becomes the right answer. Okay. Next, this one now. The quantum mechanical virial theorem for a general potential Vxyz is given by like this, where T is the kinetic energy operator and this average it denotes the expectation values of it. This leads to the following relation between the expectation values of the kinetic and the potential energy for a quantum mechanical system of the harmonic oscillator problem. So very easy one, virial theorem only you just have to use for the harmonic oscillator system to find the relation between the kinetic energy and the potential energy. Okay, so according to the virial theorem, twice of the kinetic energy, it is B times the potential energy, where B is the power of the position, power of the position. Now instead of the one dimensional, here three dimensions if they have given, that is not gonna create the impact on the value of the B, because potential energy is again half of the kx square or the ky square or the kz square of it. So we are seeing that potential is proportional to the x raised to the power of 2. So B value is gonna be 2 over here. Okay, so that makes twice of the kinetic energy, it is twice of this potential energy. So kinetic energy is equal to the potential energy. So this relationship we will be having, that makes the option A to be the correct answer. Okay. Next, this one now. Consider a particle in a one-dimensional box which is of the length A with the following potentials. X is less than 0, potential is infinity, greater than A, infinity. Then X is lying in between 0 to A by 2, it is 0. So here this box you are having. Okay, the box of the length 0 to A. The potential beyond this X is less than 0, the potential here it is infinity. Beyond this A, it is also infinity. In between, the midpoint has been considered. So this is A by 2. For the potential between V0, that is it is 0 in between 0 to A by 2, and in this region which is A by 2 to A, the potential is V1. Okay, so starting with the standard particle in a box model as the zeroth order Hamiltonian, and the potential V1 from A by 2 to the A as the perturbation. So perturbation we are applying, that is delta H value, it is V1 over here. And the first order energy correction we have to find it out. So first order energy correction, it is equal to integration of the conjugate of this wave function into the perturbation into the psi d tau of it, right? So now just substitute the values. Energy correction, it will be coming out to be psi star. Perturbation is V1 into the psi d tau. The limits are from A by 2 to A, right? Because in that region only this perturbation it has been applied. Now wave function is root of 2 by L sine of the pi x upon the L of it, right? So substitute the values. So A by 2 to A, it is root of 2 by L into the sine of pi x upon the L into the V1 root of 2 by L into the sine of pi x upon the L of it into the dx. So this V1 as a constant it will come outside. Limits are from A by 2 to A into the root of 2 by L, or its square we can say, into the sine pi x by the L, its square into the dx. So this is nothing. This is the probability values only that you are having to find the particle in the region which is from A by 2 to A only. So this is nothing. It is the probability of finding the particle. Finding particle in the A by 2 to A region. In A by 2 to A. We generally remember this value only, that is half it comes. So that means the correction in the first order perturbation, it is gonna be V1 times the half of it. So we are getting the V1 by the 2 as the energy correction. Okay, so that makes the option D to be the right answer. So if there would have been in the perturbation some x component would have been there, they are the results of the average values we use. If there is a constant value, then we directly use the results of the probabilities over here, right? Now next, CSIR exam of the December 2013. The most probable radius are for an electron in the 1s orbital of the hydrogen atom. So for the 1s orbital, the radial part we have, it is 2 upon the a naught raised to the power of 3 by 2 e raised to the power of minus of r upon the a naught of it. The most probable distance that you find, most probable distance, this we find it, take the values of the r square and the r square, differentiate it with respect to the r, equate it to the 0. What value of the r you are gonna get it, that is gonna give you the most probable distance. Okay, so now the r1s, its square, it will be 4 by a naught cube into e raised to the power of minus of 2r upon the a naught of it. So multiply this with r square and differentiate it with the r. So we will be getting d by dr of the r square into the 4 upon the a naught cube e raised to the power of minus of the 2r upon the a naught equated to the 0. So 4 upon the a naught cube is coming outside into the r square e raised to the power of minus of the 2r upon the a naught. This differentiation with respect to r we have to do it and equate it to the 0. So multiplication rule we are applying. First function as it is, differentiation of the second one into the differentiation of this exponential, which is minus of the 2 upon the a naught of it, right? Plus second function as it is, which is e raised to the power of minus of 2r upon the a naught. differentiation of the first, which is 2r, this comes out to be as 0. So I'm taking the first one on the other side. It will become 2r e raised to the power of minus of the 2r upon the a naught. This is 2r square upon the a naught e raised to the power of minus of the 2r upon the a naught. So on both the sides, these exponential terms, they will get cancelled out, right? So this 2 and 2 will get cancelled. This one of the r and one r will get cancelled out. We are getting r upon the a naught, r upon the a naught. This is not the square, here it is a naught. This value, it is equal to the 1 only. This implies r is equal to the a naught. So this is gonna be the most probable distance. Most probable distance, right? So r is equal to the a naught. Option B, it becomes the right answer. Okay. Now next, this question we are having. So again from the December 2013, the angular momentum operator, which is Ly. So cyclic rule we have to follow in this. We keep the x, y and here the z. From x to y you are going, from y to z, and z to x we go it. Now we need to find the value of the Ly operator, right? So from the y we are going to the z, so it will be z. Now remaining one, it is px, right? Z into the px minus of the x into the pz operator. So this is the value of the Ly operator. Now px value and the pz, it is z operator minus of the iota h cut del by del x of it, minus of the x operator minus of the iota h cut del by del z of it, right? So minus of the iota h cut I am taking outside. This becomes z operator into the del by del x of it minus of the x operator into the del by del z of it, right? Now multiply this and divide this with the iota. So it will become minus of the iota square upon the iota times the h cut into the z del by the del x minus of the x del by the del z of it, right? So now iota square is minus of 1, so minus minus will become plus, so it will become h cut upon the iota into the z del by del of the x minus of the x into the del by del z. So this is the value of this commutator. So options, if you see, it is minus of the h upon the I cut. Here the y is included. No, it can't be the one. Here is z del by del of x minus of the x del by z del z into the h cut by the iota. Option B is only the right answer. Okay. Next, this question now. Again, the December 2013. The question, it says energy for a single electron excitation in the cyclopropanium cation. So cyclopropanium cation, it looks like this. The energy levels in this we have like this. It is alpha plus 2 beta and the alpha minus beta. This is the one. Number of the pi electrons in this. How many pi electrons? 2 pi electrons are there. So these 2 electrons will be present like this. Now for the excitation, how much energy is required? You have to go from this level to this. So delta E will give you this excitation energy. So delta E is alpha minus beta minus of the alpha plus of the 2 beta. So it will be alpha minus beta minus of alpha minus of the 2 beta. So this comes out to be as minus of the 3 beta. So this is the energy required for the excitation. Option C, it becomes the right answer in this. Okay. Next, we are having this question now. The commutator of the kinetic energy and the momentum operator for the one-dimensional case, it is gonna be. So this question is from the CSIR exam of the June 2014. The question, commutator we have to find for the operators, which is kinetic energy and the momentum, which is px. Right. So one dimension means along the px direction they are talking. We know the kinetic energy, it is nothing but the px square upon the 2m only, right? So that means we have to find the commutator value of the px square upon the 2m, px square upon the 2m with the px, right? So the constant value it will be coming outside, which is 1 by 2m into the px square and the px. So this commutator now we have to find it out. So we know that the operators they commute with oneself, commute with oneself and its powers, and its powers. That means this value it's gonna be equal to the 0, right? So option C it becomes the right answer. Next, this question now, consider a particle which is confined in a cubic box. Okay, the degeneracy of the level, it has the energy twice of that of the lowest energy. So firstly is the cubic box. That means the energy in this it is gonna be nx square plus the ny square plus of the nz square into the h square upon the 8 ml square, right? So for the lowest level, that is lowest level, which means nx, ny and the nz, all these three values they are equal to the 1 only, right? So that means energy value it is gonna be 1 square plus 1 square plus 1 square, which is 3h square upon the 8 ml square of it. So this is the energy which is of the lowest level. Now twice this lowest energy, we have to find the level what is gonna be the degeneracy of that particular level. So twice of the lowest level energy, lowest level energy it's gonna be 2 times the 3h square upon the 8 ml square, which means the energy is 6h square upon the 8 ml square of it, right? Now the degeneracy it is equal to the n square only. So the degeneracy is n square by n square value. Okay, so n square here it is equal to degeneracy, it is equal to n square. Now in the cubic box it is nx square plus the ny square plus of the n z square, this into the h square upon the 8 ml square, this is equal to the 6h square upon the 8 ml square. Now that means nx square plus the ny square plus the nz square, this value is equal to 6. Now what values of this nx, ny and the nz we could have it, so that the energy it becomes equal to the 6. So it could be 1, 1 and the 2. So this 1 plus 1 square plus of the 1 square plus of the 2 square, it is coming out to be 6 only, which means one of the possible value of the nx, ny and the nz is 1, 1 and the 2, right? So this we can rearrange it and we will be getting the different energy levels which is gonna give us the same energy. Like we could have the level which is 1 to 1, or we could have the level 2 1 1 2 1 1. This all these three levels they are gonna give us the same energy, which is the 6h square upon the 8 ml square, which means degeneracy is 3 in this case, right? So based upon this, the correct answer is the option A over here, right? So option A is the right answer. Got it? Next, this question now. A particle in a 1D box has the ground state energy, which is E naught is 0.125 h square upon the 8 m square. The expectation values of the above Hamiltonian with the wave function psi x is given, which is x into the x minus of a. This is giving us the energy which is E1 using the linear combination of the two even functions. So here only one wave function it was there. Now the two even wave functions have been used, and this one x into the x minus of a and the x square into the x minus of the a square, we obtain the variational minimum ground state energy, which is E2. Which of the following relationships holds between E0, E1 and the E2? So E0 we know it is the exact energy. This is your exact energy. Now E1 and E2 are the trial wave functions energies. The trial wave functions energies, they are always greater than that of the exact energies, right? So that implies E0 is gonna be the least one. Now out of the E1 and the E2, the one which has more number of the variational parameters, their energy is gonna lie more close to the exact value. So we say more the number of variational parameters, more the number of variation parameters, more close the value of the energy close to the exact energy. Now in the E2 level, there is more number of the variational parameters, so its energy is gonna be more than that of the E0, but it's gonna like close to it. So E1 E0, then the E2 it will come, and maximum it's gonna be for the E1, where the less number of the variational parameters we are observing. Okay, so based upon this, option B, which states E0, E2 and the E1, this becomes the right answer. Okay. Now the next one we are having, that is this. The ground state energy for the hydrogen atom is this much, which is minus of 13.598 electron volt of it. The expectation values of kinetic energy potential in the units of electron volt it is gonna be. So total energy has been given to us, which is minus of 13.598. Now the system it is hydrogen atom, the hydrogen atom. The relation between the kinetic and the potential, we can find it using the virial theorem. Virial theorem, 2 times the kinetic energy is B times the potential. Now in the hydrogen atom, potential energies that you have, it is minus of the Z E square upon the 4 pi epsilon naught into the R. So V is proportional to R raised to the power of minus of 1. So B value is minus of 1 in this, right? From this we get 2 times the kinetic energy is minus of this potential energy. So this is the relationship between them we are getting. So use this in the total energy. So E total we know it is sum of this kinetic energy and the potential energy. So now the potential energy, it is minus of the 2t, minus of the 2t plus of the t. So this becomes minus of the t over here, minus of the t. So that means E total, it is negative of this kinetic energy. So E total we have been given, that is 13 point minus of 13.598. So kinetic energy it is 13.598 electron volts only, right? Now the potential energy, so minus of the 2 times this potential energy, or this minus of this potential energy, it was equal to 2 times this kinetic energy, this relationship that we derived it over here, right? So 2 times the 13.598 electron volts with the negative sign, this is gonna be the value of the potential energy, which is gonna be minus of 27.196. It's gonna be 27.196 electron volts of it. Okay, so kinetic is 13.598, potential is minus of 27.196. Option A, it becomes the right answer. Okay, next the phi value is given. So phi we write it as Ca phi A plus of the Cb phi B of it. The values are given. It is 0.8 phi A plus of the 0.4 phi B. Okay, is normalized molecular orbital. So it is MO. So MO diagram you have to used over here. For a diatomic molecule which is AB constructed from the phi A and the phi B, which is also normalized. So that means phi A and phi B are already normalized. The overlap between them we have to find it out. That is the S value. For the M mode, we know that Ca square plus of the Cb square plus of the 2 times CaCb into the S, this is equal to the unity. So now these values are known to us, just substitute their values. So it will become 0.8 square plus of the 0.4 square plus of the 2 times the 0.8 into the 0.4 into the S, which is equal to the unity. So we are getting 0.8 plus of the 0.64 times the S, this is equal to unity, or 0.64 times the S is equal to 0.2, or S it will be 0.2 upon the 0.64. We get the value as 0.3125. So this is gonna be the value of this overlap. So option B, that is 0.31, becomes the right answer in this. Okay. Next, if the ionization energy of the hydrogen atom is X, ionization energy, it is X. Now the energy, there is a relationship between the total energy and the ionization energy. E total is minus of this ionization energy. Okay, so that means it will be minus of the X. This is the E total. This is for the hydrogen atom, right? So that means minus of 13.6 into the Z square, which is 1, upon the N square, it is equal to the minus of the X, right? So we can say from here that the value of 13.6 upon the N square, this value is equal to the X, right? Now for the ionization energy for the lithium 2 positive is being asked to us. For the lithium 2 positive, firstly E total, it is minus of 13.6 Z square upon the N square. Now the Z value for this, it is 3. So it will become minus of 13.6 upon the N square into the 3 square of it, right? Now this value, which is 13.6 upon the N square, it is X only. So total energy, it is minus of the 9X, right? Now the ionization energy is being asked to us. Ionization energy for the lithium 2 positive, it is negative of this, negative of the minus of the 9X, that comes out to be as 9X. So this is gonna be the ionization energy for it. So option C becomes the right answer. Okay. Next, we are having this one, simple Huckel molecular orbital theory. The first statement, it says it considers the electron-electron repulsions explicitly. No, it is not considering that. It distinguishes between the cis and the transbutadiene. Again, the incorrect stereochemistry cannot be determined using the simple Huckel molecular orbital theory. It distinguishes between cis-butadiene and the cis-butadiene. This is the correct one. Because if you see, this is cyclobutadiene. Here the bonds between the carbons, it is different. 1, 2, 3 and the 4. Between 1 and 4, the connectivity it is there. Whereas in the cis-butadiene, that is this 1, 2, 3 and the 4. In between 1 and 4, there is no bonding. So that means different secular determinant it will be found. Different values of energies we will be getting. So we can distinguish between these two. Right? Next. This one, a particle in the one-dimensional harmonic oscillator in the x direction is perturbed by the potential which is lambda into the x, where lambda is a number, the first order correction to the energy in the ground state. So correction to the first order, we have to, of the first order we have to find it out. Delta E for the first order, it is equal to psi, the perturbation that you have, into the psi, the get notation. This is equivalent to integration of the psi star into the perturbation into the psi dx, because SHO we are talking, so this can be written. So now here it is psi star into the x into the psi into the dx, lambda times the x. So here you see, for the SHO, if you have this odd power, so x is raised to the power of 1 in this. So if you have the odd powers of x, odd power of the x, if it is there, then the energy correction term, it comes out to be 0 for the first order perturbation. So this scenario is for the simple harmonic oscillator only. So this we already remember these things. So that makes the option A to be the correct one. Okay. So this was the last question that was to be discussed in this part. So we have discussed the paper of the 2011 June and the December, 2012 June and December, the 2013 June and December paper we have discussed, and for the June 2024 some of the questions we have discussed. We will be seeing that if some of the remaining questions are there for the June 2014, that too, and the remaining questions that you are having for the remaining years, that in the upcoming parts we will be discussing. Okay, so thank you so much for watching. I hope all these questions they are clear to you. If you have understood the concepts, then make sure you hit the like button for the video and do share it with your friends as well. And if you have not subscribed to the channel so far, make sure you subscribe to the channel also, so that you can get notification for the upcoming parts too. Okay, so thank you so much for this one. We'll be meeting you in the next part now. Okay.